Okay, well, first of all, let me welcome everyone to the San Diego Independent Scholars monthly lecture series. This is a monthly set of webinars that we offer on Saturday of the month at 1:30. Now, if you are not receiving notices about this, go ahead and put your email address on the chat, and we'll include you in the list so you'll know. So I'm Jamie Panetta. I'm the program director for SDIS. And I just have a couple of housekeeping announcements before we get started. The first is that let's hold off any questions. Well, I think Tom wants to have at least a Q&A halfway through and then another at the end, I believe. But
that's pretty accurate.
Okay. All right. But, if you have any questions in between, feel free to ask, especially if it's to clarify something. But hold them off until the Q&A. And then for the questions, we'll try to use the raised hand or raised hand function, where you press the button and a hand comes up, and we'll know who is trying to ask a question, and then we'll call on you. And at that point, you're going to have to unmute yourself, okay? This talk is being recorded, and it will be posted on the SDIS YouTube channel. And if you see at the bottom of the slide here, there's a link, www.sdscholars.org. That's the website, and there you can find the link to the YouTube channel and the talks. Was there anything else that we needed to?
I don't think so. Let me mute everybody right now, and then Tom, both of you will have to unmute yourselves.
Dr. Tom English, and we're very fortunate to have him be our speaker. Tom has, as you can see in the slide, is a very sought-after speaker. He's been to the White House 8 different times giving presentations on the climate crises. He's lectured at over 100 universities. He has studied high-level nuclear waste programs for President Carter's OSTP program. He's worked for Sweden, NASA, and the California Energy Commission. He directed the EPA, $80 million a year on the Energy and Environment Program. And he is the author of the California Clean Air Act.
Wow.
Currently, he's the creation care educator at the Presbyterian Church. So again, we're very, very fortunate to have Tom come talk to us on the climate crisis. So I am going to turn it over to you, Tom.
Okay, thanks very much, Jamie. Really appreciate it. I think you're going to enjoy this talk. It's one I put together recently. It's basically addresses the climate crisis, and it's kind of a policy kind of talk, a religious kind of talk in some sense. It says, can we successfully resolve the climate crisis? Now, some people are saying, what crisis? That's one school of thought. Other people are saying, oh, we're doomed. There's nothing we can do. So I'd like to help you sort your way through those two different pathways to get some sense of reality into what we can really do, what the crisis really involves and what we really can do about it. So that's what we're going to be aiming for. And I'm going to use a technique here that's kind of cute. This will be a discussion of who does things, what do they do, why are we in this crisis, when did it occur, where are things going, and how do we get out of it? So that's the basic roadmap we're going to be following. Many have called this crisis an existential threat to our civilization. Now, by existential threat, you can mean a lot of things, okay? What we mean by this one here is that if we don't solve this crisis in a timely manner, this could mean the extinction of humanity as a species on the planet Earth. And we're not talking about a time scale of 1 billion years from now. It could be as early as this century. So it's pretty hot stuff. and it really is very motivating. So we basically, it turns out the thesis I'm going to tell you is that we have both the favorable technology. We have the tools to solve the problem. The economics looks beautifully good. So we basically have the technology and the economics needed to solve this crisis. The question is, do we have the will? So we encourage your participation during this because I think this could be a very lively discussion. This is the, I think I referred to earlier, this is Rudyard Kipling's, it's from The Elephant Child. And it says, I keep 6 honest serving men. They taught me all I knew. Their names are what and why and when and how and where and who. So this should be enough to take care of most issues. If you can go through these questions and come up with decent answers, you should know something. This is the roadmap for how we're going to go during today's talk. We're going to have a section where we talk about what's going on and where is it happening. And then we're going to have a little break. Then we're going to talk about why things are happening and when they're happening. And we're going to the how to fix things and who can do it. So that's the basic roadmap. And we'll put this up from time to time as we go along. First, we'll start with what and where. This is a throwback to the Wizard of Oz. There's Dorothy there. I don't think we're in Kansas anymore. And there's the scarecrow saying, you're right, it's New Hampshire. So all of a sudden we are seeing really weird weather all over the planet. What in the world is happening? I mean, this doesn't appear to be a repetition of anything I've seen during my lifetime. And it turns out it's not. So we're into a new era here. We have to figure out how to thread our way through this era. This is a clip from CNN in October. It basically says New York City this morning was having the worst air quality in the world. You know, that used to be reserved for Beijing. So now it's New York City. And what's causing all that air quality? This is the city here. You can't even see it. And the thing that's causing it is about 5% of Canada is burning. So these things that we're getting, these fires and such, are not small scale little things. They're enough to basically threaten a whole nation and cause transnational problems. Also, while this is going on the same day, the temperatures in the West were breaking all kinds of records. Sacramento was 106. Death Valley got up to 126. So the whole Southwest was baking. And so again, these are record-breaking numbers. So there's something strange going on here. Basically, this is another clip from CNN the same day. It was a busy morning for CNN. They say the climate crisis is causing record heat, rain, flooding globally. So the whole planet is involved in this thing. It's just not a local kind of problem that occurs freakishly, once in 1,000 years, once in 10,000 years in some corner. It's the whole planet that's taking part in this. Now, to make some sense out of this, I'm basically going to take you back to my early days in environmental work. I had just finished my postdoctoral degree at Vanderbilt, and I was working for the Environmental Protection Agency. And there was a nice conference at the University of North Carolina in Chapel Hill where they gathered together the main global experts on climate change. So it gave me a chance to spend the day with these experts and see what they knew about climate change. This is back in around 71. And it starts off pretty well you'd expect. One of the professors gets up and says it's going to get warmer, and I'm nodding my head, yeah. And pretty soon another professor gets up and he says, it's going to get colder. So I'm a little confused by now. And then they make it even worse. One of them says it's going to get warmer first and then get colder. Another one comes up and says it's going to get colder first and then get warmer. So, this mass confusion here. They can't make up their minds as to when should we see any impacts. Is this going to be like in 10 years from now, or is it going to be 1,000 or 1,000,000 years from now? So basically, it's just total mass confusion. So that's where we started the climate crisis instead of mass confusion. So since then, it's been about a half century. We spent billions of dollars and employed thousands of engineers and scientists. And so let's take a look to see what we have learned about this and whether we can apply some of that learning to actually doing something about the problem. So global warming, the first theoretical paper that was written on it back in 1896 by a guy called Svante Arrhenius. He was one of the founders of the Nobel Prize Committee. Anyway, he basically said if you burn a lot of fossil fuels, it'll cause the carbon dioxide to rise, and the carbon dioxide rise will cause global warming, which he thought was a great idea. This is a guy who lives in Sweden. And so basically he thought global warming sounded good to him because the winters were much too cold up there. So that's where we got started. And then it sort of died in public interest for a long time. And then in the basically the early 60s, this guy, Charles Keeling, he's a guy from Scripps Institution of Oceanography, had a passion for measuring carbon dioxide. He wanted to measure it better than anybody else on Earth could measure it. And he also was a slick salesman because he was able to get the university to pay him real money for working on a mountainside in Hawaii. So what a clever guy. So what he did is he starts measuring the carbon dioxide there, and he finds out something interesting. He finds out that the carbon dioxide goes up in the winter and goes down in the summer. Then the next winter it goes up and then down. It's like the Earth is breathing itself. So what's happening here is that in either hemisphere, this is the northern hemisphere, in the summer, you just have more green plants, and the green plants love to eat oxygen. And so they're basically causing the drop in the oxygen. And then in the winter, the plants aren't as active, and so the oxygen or the carbon dioxide goes up. So that's basically the curve. And Keeling didn't get in any trouble over this curve here. But what they got in trouble over was, notice this curve is sloping upward. This means that there is a global increase in CO2 concentration, and this got the immediate attention of the fossil fuel industries. And so they started attacking Keeling's work as being worthless. Everybody knows you shouldn't set a measurement scheme up on the side of a volcano. They basically tried to do everything they could to discredit this work. And so the compromise that was made up was they decided, well, we'll put the same kind of equipment out in 7 places on the Earth, somewhere near the North Pole, somewhere near the South Pole, somewhere in Russia, like Vladivostok, other places, 7 places, and then we'll run the data for a while and see whether or not Keeling's data is any good. So they ran it, and they essentially got the same data in all 7 sites. So all of a sudden, Keeling goes from a questionable character to one that isn't impeccable. And here's where we are today. Basically, that's been going on since the 1960s, and here we are in 2024. This was done in January of 24, the last data. And you can see that there is no irregularity in the CO2 concentrations. It just keeps going up and up and up. So what happens is, as it goes up and up and up, these are small concentrations of CO2, but they're very powerful concentrations, enough to affect the temperature of the planet. We'll talk some more about that. So basically, this is what's happened in temperatures going back to the post-Civil War era. Basically, what we can see here is that during this period of time, from the 1900s to around 1940, that things were pretty much heating up. Pretty nice trend there. Then what happened is World War II occurred. And World War II was characterized by burning a lot of things, setting a lot of bombs off. And so what happened is we got a lot of clouds all over the planet. Clouds act as a reflector for sunlight. And so if you put a lot of clouds in the air, what it does is it tends to cool down the planet. So we got this period of cooling during World War II, and afterwards there was a lot of prosperity. And so what happened is we basically created more clouds through our prosperity. And then we did some things that caused the clouds to go away, like the Clean Air Act. And what happened then is that worldwide, they started to get the idea to clean things up. And so all of a sudden we have a big rise in temperature that's going steady. So that gives you a feeling for the time since the post-Civil War. Now, if we want to go back further, because people might argue, some climatologists might say, this is not enough period of time to be able to see any real issues here. Let's go back a little bit further. But let's see where we are today first. So this is 2023, the year that just ended, and it turns out it's the hottest year on record. So one sparrow does not a spring make, but this is 1 year where it's really hot. So let's look at the surrounding years. Okay, 22 of the last 23 hottest years on record have occurred since the year 2001. The one exception is 1998 snuck in there. So we have a pretty long series of record-breaking global climate temperatures. So it tells us something's going on here. To go back further, we need to get some sort of time machine. Let me give you an example of the time machine. This is a time machine, a cross-section of a tree. You can look at the cross-section of the tree and measure from a dark spot to a light spot, and that tells you it's a year. And you can measure the thickness of the light spot, for example, and you can get some idea of what the moisture was. So this is a sort of a not super accurate, but an okay kind of tree ring. But for this work we want to do better than something like this. So let's do the best we can. So let's do something that involves ice. So what we do is, if we're in an area where glaciers are forming, is what happens is it snows there, and the sun comes out and tries to melt the snow. But in those areas, it doesn't melt all of it. It just basically hardens some up on the surface, causes it to be a little bit more dense, and then it snows again for the next year. And so what you do is you get a series of little lines here. These are lines of high density ice. And these lines pile up. So by basically taking a core of ice and basically getting that core, and then taking the core and putting it into something like a bologna slicing machine, you can slice up little pieces and you can examine what's going on in over time. And some of these cores are about 2 miles in extent. So we can go back pretty far. We go back about 1 million years. Here's an article from Science that says we can measure nitrous oxides back to about 650,000 years. So that should be long enough to satisfy anybody's need for a trend. And well, we can also measure CO2 even further back. So you can see this what happens is when you drill these things deep enough, you start to run out of the glacier. You start to hit bedrock. And so you have to stop it at some point. And this is what the slices look like here. Basically, you take a slice here and you basically give some of it to your friends in chemistry. Some of them are going to measure gases. Some people are going to measure the physical properties like pollens, spores, etc. Some will do radioactive measurements of the isotopes. You measure everything you can think of with that. And then you plot the data against something else. So this is an example of the data being plotted for temperature going back about 800,000 years. This is where we are today, 0. And this is 400,000 years. This is 800,000 years. And this is temperature. There's some so-called zero temperature line here. And then basically this shows temperature going up. This is temperature going down. So up, down. So what we have is basically a period here where humans have existed. From this period peak here to this peak here, this is about the time of humanity existing. It's about 150 million years. So that's called one ice age. So in this data here, we see about 8 or so ice ages. So this is pretty darn good data. So then what happens is, since we can measure the temperature, let's see what else we can measure. So one of the things that they measured along with that is the carbon dioxide in the ice. And notice this is very interesting data. As the temperature goes up, the carbon dioxide goes up. So it looks like carbon dioxide might have something to do with causing the temperature. Whenever the carbon dioxide goes down, the temperature goes down. And so it's got a pretty good a relationship. It's not a one-to-one, because it turns out there's another variable at least involved in this, and I'll show you that a little bit later. But it's very clear that there is some relationship between carbon dioxide. This is this blanket of stuff, of heating material that covers the whole planet, and the temperature. So, but interestingly enough, notice the temperature never gets below, or the carbon dioxide never gets below a certain number. Let's call it 180. Okay, 180 parts per million. It never gets above a certain number, 300 parts per million. So the planet Earth, for the last million years in this data, has never been outside of this safety zone. And it turns out, if we go back in time a little bit further, from this data goes back about 3 million years. So for 3 million years, the planet Earth has never been out of this safety zone. So if we're trying to manage the planet Earth, which is what we're doing these days, we're now the biggest species, most powerful species on the planet, we should know something about how the planet works. So this is one of the key things. We should recognize this planetary boundary, that the CO2 shouldn't get too low, because if it gets too low, what happens is the Earth turns into a giant snowball. The oceans all freeze up and you have a big snowball. So you don't want to get it much below 180. You don't want to get it above 300. So where are we today? Well, there we are today. This is our safety zone here, and we're up here at about, in these units, about 420. So we're well above 300. We're about the width of the safety zone away from the safety zone. So when Roger Revelle saw this data, he said that we are conducting this worldwide uncontrolled experiment, and his comments were kind of clever. He wished us well. So it's really humanity being rather unbright in allowing this to happen. So if we also look at another gas that's in the ice data, it's methane, the stuff that cows belch, for example, and that leaks from natural gas pipes and so forth. We see the same kind of thing. Wiggly lines going up and down with the ice ages. As the temperature goes up, the methane goes up, and so forth, goes down, same kind of pattern. If you look at the details, this pattern is different than the pattern for CO2. So this accounts for some of the variability in the temperature that we could never understand before. So it's a very similar pattern to carbon dioxide. And here, the methane here is even further. Instead of being one width out of this safety zone here, it's 3 widths outside of it. So we basically need to get our act together and have some kind of standards, global standards, for both carbon dioxide, methane, and also the other greenhouse gases. If we don't get those standards, we're not going to solve the problem. Right now, we don't have those standards. So here's what the greenhouse gases look like. This is carbon dioxide, about 2/3 of the problem. There's methane here, about 17%. Then we have some other gases here. So we desperately need to get planetary standards for these greenhouse gases. So all of a sudden, we have some evidence that I think is pretty clear that the temperature future of our planet is being determined by us. Not in a planned way, but in a hands-off way, where somehow the invisible hand of Adam Smith is going to solve all this for us. So we have to do better and come up with some conscious approach to solve the problem. So we're the first part of the questions. So any questions so far? I hope I've gotten your minds a little bit excited here. and I'd be delighted to have a few questions. Well, if not, let me ask you a question. Does anybody think it's important to?
Oh, Alvin has a question here.
Oh, good.
Go ahead, Alvin. You have to unmute yourself.
Yeah, so the question is this, and the way you said it a couple of times don't sound that way. That's not what you meant, but it's cause and effect. So the question is there a feedback loop between this temperature rise and the amount of CO2 and methane are in the atmosphere? So one can argue, well, you know, maybe the temperature goes up and therefore the CO2 and the methane go up, and maybe, or at least there's some correlation or interaction between the two that feed on each other. So what do you say about that?
Well, clearly there is going to be feedback in these complex systems. And so what we have is a host of several thousand modelers running about, at least a dozen different major models to do these kind of calculations. And what they show is that indeed, these greenhouse gases should cause the planet to increase in temperature. Even the people involved in the space effort get involved in that. And what they find is that, for example, there's the greenhouse gas of carbon dioxide causes incredible temperature increase for the planet Venus. It causes a moderate increase for us, which is we're lucky because otherwise it'd be a big snowball. And there isn't much CO2 on Mars, and so Mars is a very, very cold planet. So we're getting verifications, from the planets. So yeah, they understand pretty well the feedback system, because what we're seeing here is not a subtle kind of phenomena. It basically is, if you're putting tons and tons and tons of stuff into the atmosphere, something's going to happen with it.
Thank you.
I hope that helps.
Thank you. Thank you.
Got it.
Any other questions? Okay, well, maybe we can get them at the end here, but I'll move along to the next area. So now we're getting to the why and when. So we basically talked about, hey, this is a planetary kind of problem. The problem appears to be very serious. We need to do something about it. To better understand the present threats, let's look at some past crises that killed a very large number of species. Let's look at mass extinctions. So this is a summary of the 5 mass extinctions that have occurred in the history of the planet Earth. Basically, a mass extinction is defined to be some phenomena that occurs, some set of phenomena that occur that cause the extinction of more than half of the plant and animal life on the planet. So that's the definition of a mass extinction. So more than half. There's been plenty of other smaller extinctions, which I'm not going to bother with today. I just want to get the main ones out of the way, mass extinctions. So what happened is, back here about 600 million years ago, life was fairly simple. And something strange happened that we don't quite understand yet. It's called the Cambrian explosion, where all of a sudden there was an explosion of life, of different forms of species that just seemed to pop out of nowhere. And that over about 100 million years grew and grew and grew. And then something happened, something went wrong. And what happened is half of those plant and animal species went extinct. So that's called mass extinction number 1. Well, we recovered from that. Recovery takes typically about 10 to 20 million years. And what happens during recovery, basically there are sort of job opportunities or niches in the ecosystem that were wiped out by the mass extinction, because they didn't have species to fill those jobs. And so species that are left move around, mutate, and change themselves, whatever. and a new set of species replaces the ones that were there before. The old ones never appear to come back. So you have a new set here. And so basically you start to get up to a peak here. Things wobble around for a while, and then another mass extinction occurs. This one was caused by the atmosphere, by things like carbon dioxide in the air. The first one, we don't really know for sure what caused that. So we do know what happens with extinction number two. Number three was the worst of all the mass extinctions, the so-called end Permian extinction, when we almost lost all of life on the planet. And that again was caused by basically carbon dioxide, greenhouse gases in the air. So that kind of thing where the greenhouse gases get high enough to make a big difference has occurred several times in the past. This extinction here, number 4, was similar. And then we have a nice growth here where we create the dinosaurs, and the dinosaurs are ruling everything in the so-called Mesozoic area, which means between life area. Paleozoic means old life. Cenozoic means recent life. So basically this is in between here. So we have Barney and the other dinosaurs here. And then a big rock from space about the size of the Himalayan mountains hits the Earth somewhere near Cancun and near Club Med in Cancun, and makes a big hole in the ground about 100 miles across. And it causes molten material to be thrown into the stratosphere, and the stuff glows and causes fires over the whole Earth. And that's enough stuff to kill off the dinosaurs. So the dinosaurs go extinct. And so these little guys here, these mammals who could hide somewhere, they were able to survive all that. And we came out of that group. And so this is the current era. And here we have a dip in the current era that's coming down here. And so people were saying, are we in the beginning of the 6th mass extinction? And they're calling this era the Anthropocene era because we are now the #1 species on the planet. What that means is that we are responsible for more biological impact and more geological impact than anything else on the planet. So we're #1. So whether this is ends up as a mass extinction or not, it's going to depend on what #1 does. How do we function in this time? And we're having a tough time coping with the problem. So I'll try to help you with maybe some ideas on that. One of the things that's causing the mass extinction is being caused by 2 things. One of the things is the destroying of the tropical rainforest. In the tropical rainforest, you have more than half of all the species on the planet. And about half of those only exist in the tropical rainforest. So what you have here is a graph showing the percentage of the tropical rainforest. I started it in 1990, and basically that's 100%. And we're losing somewhere between 1% and 3% of the tropical rainforest every year. So I picked a number of 2%. And this data fits pretty well for the last, whatever that is, 30 years or so. So I think the data is pretty good. And the trajectory is that we basically are going to do in the tropical rainforest somewhere in the 40s, 50s or so. So what happens whenever we do, well, why would we care about tropical rainforest? Well, if you got half of all species there, and more than half of those are endemic, what happens to the species if their home is taken away? Well, they go extinct. So this phenomena by itself can account for a 25% extinction of plant and animal species, 25% due to the tropical rainforest. This is that thin layer of the atmosphere. The Earth's about 8,000 miles across, and this is a very thin atmosphere here, I don't know, a few 100,000 feet. It turns out if you put enough stuff in there, the concentration of the stuff gets high enough to make an impact. This is the way that the sun works. It basically heats up things here. We don't get too hot because we radiate a lot of this heat back to space. But as we build up this blanket, this atmospheric blanket, what happens is a lot of that heat gets reflected back to the Earth. And so the planet starts to warm up. And so that's our problem that we have today, that our blanket is getting too thick, and it's getting too thick for the ecosystems that are on the Earth and the species on the Earth, including us. This gives you some idea of the growth of emissions of carbon dioxide going back to the 1850s. You see, there wasn't much then. So it's a fairly recent problem. And it grows up and up and up and gets really high here. So what we've done is we basically exceeded the assimilative capacity of the atmosphere for these pollutants, CO2 and other greenhouse gases. So we're basically spewing 142 million tons of man-made gases into the thin shell every 24 hours. So we treat it like it's an open sewer. And you can get away with that for a while, but we're well past that. This is what I mentioned earlier. This is the planets. This is the sun. This is the Earth. Here we have Venus. And this is the atmosphere of carbon dioxide represented on Venus. It's a very thick atmosphere. The pressure of the CO2 would be such that if you were a human, you would be crushed on the surface of the Earth, of Venus. This is the Earth with the just right blanket. And this is Mars with too thin of a blanket, so it gets too cold there. So there's the temperatures. The Earth is about plus 15 degrees C. Venus is 464 degrees. So you can see, and Mars is minus 65. So this blanket makes a big difference. There's Mercury, 167. It's just, it has essentially no blanket, but it's really close to the sun. The second threat is basically that of temperature. This is a cover of Nature magazine, founded by Darwin a long time ago. And this cover is this shows a lizard here, and it's titled Feeling the Heat. If you get an article in Nature, it's like, wow, Tom has an article in Nature. That's really great. If you make a cover story of Nature, your career is made. So it's really a prestigious magazine. And basically this article, Feeling the Heat, was the result of the works of about 20 major scientists. They did a sample of over 1,000 land plants and animals, and they found out that most of their data fits in between 15 and 37% of the sample is committed to extinction by 2050. So that's this century, committed by run-of-the-mill routine climate change, not the extreme models. This is the right in the middle of the projections. So this says that, hey, this could be another 25% extinction caused by temperature. So if we take the extinction due to the temperature rise, plus the extinction due to the tropical rainforest destruction, we end up with 25% plus 25%, 50%. We end up with a mass extinction sometime this century. So that's kind of the basic science behind it. This is a guy, Jim Hansen, who's basically appeared before the Congress more times than anybody else on climate change. As he did his PhD thesis on the planet Venus, so he knows something about CO2 and the planet. Anyway, Jim is one of the world's experts in terms of understanding the mechanisms of climate change. He tries to put all this together, and I'll try to give you some indication of how he does it. In doing a model of the Earth, he basically takes the Earth and divides it up into little squares, about 200 red squares, about 1,000 miles on a side. And then he takes each of those squares and divides them up into 7 squares across here. So each of these is 160 miles across, essentially. And what he does is he makes the measurements of the temperature there in each of the green squares. So he's basically one set of measurements will require about 10,000 green squares. So he's really putting a massive amount of data into a computer model and trying to give you some indication of how temperature affects things. And he does this every day for 10 years to get essentially one data point. So to understand the data, we'll go back to an old bell curve that we were all familiar with from grade school. You know, some of us get A's, some of us get F's. And basically, this is the scoring system here. We have some sort of distribution. We like to call it a Gaussian distribution. And so we'll use that technique to basically understand what Hansen is saying in his data. So this is the measurements that he did there with those precise data every day for, he would break the data up into decades of the 50s, decades of the 60s, of the 70s, and so forth. So he does this here for 30 years. And this data here shows that during that 30 years, that this the frequency of temperatures occurring didn't change at all. It all fit right on this curve here. So what happens is he's trying to describe all the days of the year, and what he finds out is that the so-called higher temperatures occur only between 2 and 3 of these thicknesses of the distribution, the so-called standard deviation. So that's very stable from 50 to 80, and he speculates it's been stable for 100 years more backwards. So let's see what's happening to that today. Oh, this stuff under here doesn't stop at 3. The curve goes lower and lower and lower, but it's still there. So there are some weird phenomena that occur one day a century, these outlying kind of phenomena. And then there are some phenomena that occur maybe 3 days in a million years. So really outlying phenomena. So we're going to show you what happens if this curve moves around, what it does to the outlying phenomena, and we'll show you how that affects you now. So this is what his data looks like when you put it all together. Is the curve here, blue meaning colder than average, white meaning somewhere in the average, red meaning warmer than average. And basically his data all fits under the green line here like this. And notice there's nothing that you can see out here above 3, nothing, because it's just so rare. So that's the baseline that we're going to work with. This is baseline data from 50 to 80. Now, so these would be called extreme temperatures over greater than in 3 sigma, 4 sigma, so forth. These extreme temperatures occur over less than 0.1% of the Earth. So they're pretty rare to see these extremes, okay, during this time, 50 to 80. Now, let's look at 2001 to 2010, the decade there. And what's happened is we now have a different color. We have the red, white, and blue we had before, but now we have a yellow. And the yellow, it would be called extremely hot. Notice that yellow data is all above 3 sigma. 3 sigma, 4 sigma, up to 5 sigma. So what's happened is we now have extreme temperatures over 10% of the Earth instead of 0.1%. So the coverage of extreme temperatures has increased by a factor of 100 over what we would normally expect with the green curve. This is a remarkable change that we're seeing here. So it means the Earth is becoming different than it was before, significantly different. Let's look at the details here. Again, this is the normal behavior here. This is the planet Earth, nice and blue for the 3 decades, 50 to 80. This is that stuff that occurs 8 times a year here. So let's look at the curve from 2001 to 2010. That curve is in pink, and notice it's not as high, so it's come down its peak, and it's a little fatter, okay? But it's also moved to the right. So what we're doing is we're now seeing the phenomena that occurred here 8 times a year occurring 8 times a year, except this is the phenomenon that used to occur once in a century. So that's why you're seeing all these record-breaking floods, record-breaking heat waves, so forth, record-breaking hurricanes, because we've shifted this curve over. So we now have essentially a different Earth than we did before. And we're making it more and more different. If we make it different enough, it's not going to be pleasant to be living here. So the Earth is very different. This is a picture of the New York subway during Hurricane Sandy. And basically the water is pouring down the stairs here, and it was a mess. So you can have problems like that in a city like New York, and it costs a lot of money to fix them. So what happens is if these hurricanes don't occur too often, then what happens is you can go ahead and fix them, and it's not going to ruin the city. So let's look at the Hurricane Sandy and look at some of the data. Basically, back in 1880, using the calculations, they expected a hurricane like Sandy to occur once every 500 years. So that gives you a lot of time to basically fix up whatever went wrong during that hurricane. Sandy occurred in 2017, and they're saying here this is expected to occur once in 25 years. So you still have some time to fix up all the damage, okay? But they're going out here to 2030, 2045, they're expecting that once in 5 years. And so you probably can get to a place where you can't afford to repair New York City. It just is getting to be too expensive. So what you can do if this problem occurs more and more often is you have to abandon places like New York. So it's a good idea to solve the problems before it gets to that extreme. So anyway, that should wet your whistle a little bit. Any questions about any of that?
So I have a question. So the mass extinctions that you talked about, the second and the third, were also caused by increases in CO2. What were the main sources of that CO2? I didn't know humans weren't around then.
Yeah, what they find out is that it's volcanic activity. What happens is you get things like the Trapin Flats in Siberia, and it takes maybe 10, 20,000 years to create these flats. This is large, massive basaltic areas. And so whenever you have those giant cracks in the earth like that, then what happens is you get all the CO2 out. So if you have these cracks that last long enough, what happens is you can basically cause a big problem.
So we're seeing some of that even now, right? Volcanic activity and things like that. So what percentage of the CO2 is produced by that nowadays?
Well, that's something the modelers have to look at. So they look at the data and they say, gosh, there's a whole lot of CO2. But if you compare the amount that's belching out of like in Iceland last week, there was a big crack there and the volcanoes were belching. That turns out to be small compared to the amount that we're belching out. So basically, the Earth is set up, it's a good design, so that there is an assimilative capacity that can take a certain amount of that stuff and no problem, it just handles it. The things around the volcanoes get rich soil and it becomes a great place to plant things. The air gets acidic for a while, but then it rains out. And so the problems don't last very long. But if you put so much in that you can't, you swamp the repair mechanism, and what happens is it starts to build up.
Thank you.
Okay, any other questions? Okay, super. Let's move along to the next part.
I think Alvin has another question here.
Oh, go ahead, Alvin.
You have to unmute. Alvin, you're muted.
Yeah, so I in reading about a lot of this stuff over time, it's clear that in addition to the sort of slow, steady rise in CO2 and the associated temperatures, there are also things that are sort of like critical points, something like phase transitions that people are scared about, in which you reach a certain point where something happens that's irreversible. That is to say, you go into a positive feedback loop that is so intense that it changes things in a very, very drastic way, rather than a gradual way, such as, for example, something occurring which suddenly, over a period of maybe 50 to 100 years, changes the Gulf Stream, something like that. and things of that nature, or the positive feedback occurs so rapidly that and it has an effect which is so drastic that it's going to obviate the possibility of addressing these issues. Could you speak a little bit about those possibilities and what people think about them these days?
Sure. Yeah, that's a great topic. As we go back at these mass extinctions and you look at those, what you see basically is that the Earth's let's say thermal system jumps from one state to another stable state, and basically stays in that stable state for a long time until something causes it to jump out of that state. So that's happened 3 or 4 times in our history that we know about. So we know it jumps from state to state, and the states may be different. I mean, there might be a whole bunch of states out there, and it just sort of picks one and goes for it. So that's something we think we have a little bit of an understanding of now. 30 years ago, we had no clue about that sort of thing, but I think we know a little bit more now. So there are these stable states. And when they talk about a tipping point, what they're talking about is basically kicking the planet out of one stable state into another stable state. So a lot of the stuff that were advertised as tipping points really aren't tipping points. They're just, bad things that are happening. But if you have enough bad things happening, enough to kick the system from one state to another, then you're going to be stuck in that new stable state for a long, long time. So it's basically like this, like a chaos theory, I guess is how you'd call it. You basically go from one state to another, and we now know enough to model that there are other stable states. And we know that if you kick it enough, what happens is you'll jump out of one to another. So that's what we're hoping to avoid having happen. This doesn't mean that you have a rose garden during the stable state that you're in, because you can make it miserable enough where you don't care about whether you jump to another state or not.
Thank you.
Sure. Okay, good. Let's move on to how and who. Now, this is giving you it's kind of like having to take a drink of water from a fire hydrant. But I thought it might be fun for you. It was good exercise. So basically, here we are. Scientific American says, we are now number one. We are the number one species. We have conquered the planet. And I agree with that. We've done it. It's interesting that it says the weapon our species used to conquer everything is not survival of the fittest, it's cooperation. We're able to cooperate with each other in such a way that we can essentially run the whole planet. So there we are. And since we have already significantly damaged our world, can we successfully resolve the crisis? That's the real question behind us today. We've already made a wreck of things, and if the wreck's getting worse, can we fix it? So I'll try to resolve that in this section here. So this is an article that appeared in the KPBS letter. It's basically how a San Diego scientist helped shape the Pope's climate change plans. And it should go on to say, and then that shaped the world's climate change plans. So this guy here is Ramanathan, Professor Ramanathan. He's been at Scripps forever, and he's probably the leading climate guy in the U.S. And this guy here wearing the white outfit is called the Pope. So what Ramanathan did is he organized a bunch of his buddies from UCSD to go to Rome. About a dozen of them went. And they went to meet with the Pope's Papal Academy of Sciences. This is about 100 guys that basically advise the Pope on scientific issues. So that's the idea. So Rom brings a bunch of guys with him, a dozen guys from Scripps, etc., to meet the Pope. And while they're getting ready to go into some fancy room with tapestry lining the walls and everything else is being all set up, the Pope drives in with the Pope Mobile. So he's driving his little Pope Mobile. He gets out of the Pope Mobile. He's wearing this white outfit. And so this guy back here says to Rob, he says, "Hey, would you like to meet the Pope?" So this is called the parking lot meeting of Rom and the Pope. And so they meet, and Rom is given 2 minutes to explain to the Pope what the issue is. So he talks to them for about 2 minutes, and then what happens is they all go and meet with the Academy, and then the Pope has days to spend with them. So it really made a difference, made a big difference in terms of the Pope's view of things. So it was really good that these guys did. Charlie Kennel, who used to run scripts for, I don't know, a dozen or so a year, said this is the most important meeting he's ever been to in his life. So it's really a key meeting. So basically, that's the parking lot meeting. And this gets the Pope interested in doing something. And so he gets Cardinal Turkson to help him write this encyclical. Encyclical means a letter. It's usually addressed to somebody or other. This is the first one ever addressed to all of humanity. So they write this encyclical to all of humanity on our common home, how to take care of it. And this is basically a plan for how do you solve the climate crisis. So this plan becomes very popular. Many people read it. It leads to a meeting in Paris of the United Nations. And that meeting, basically, they all agree on this stuff here. So what happens is they come up with the so-called Paris Accord, which is an agreement that says we need to do something to fix the climate problem. So basically, it's kind of interesting. The local guy here had basically changed the world in terms of the climate issue. Now, in terms of environmental laws, there's basically, in terms of things that are recognized, there's so far before this, there was only one environmental law was affected the whole planet. That was the so-called atmospheric hole in the ozone layer. So that was one law. This is the second environmental law that we have. We only have two. So basically, this is the second worldwide environmental law. So that's pretty good for a UCSD guy. So what they basically came up with in this is a description of what things were going to be like and what things would be like if we fix things a little bit. So basically, this is a curve here predicting the emissions of carbon dioxide and other greenhouse gases, starting from where they are, and it's going to go up like this. Now, this is what they call the business as usual curve. This means you get a whole bunch of modelers, economists, whatever together, and you predict what the future is going to be like. And this is the middle of the curve. Okay. So they basically say, okay, between when the meeting takes place and say the year 2100, the temperature is going to rise in effectively 4 degrees from some baseline, 4.6 degrees. And that turns out to be a big number. 4.6 degrees is a giant number for an ecosystem. So what they did is they fought each other, which they normally do, and 195 nations came up with an agreement that what we would do is we would pledge to not make it this bad, but we would pledge to make it this bad. So only 3.5 degrees. The goal that they were shooting for was 2 degrees, but they didn't have the horsepower to get that goal in terms of pledges. So basically, they were saying we're going to make it not 4.6, make it only 3.5, and there we are. Okay, and hopefully someday we'll get down to 2 degrees. That was kind of the result of the Paris Accord. Now, this is 2015. We're a little bit later. We now have another COP28 going on. That was 8 years ago. So how are we doing today? So looking at the same curve, we took this business as usual curve here, and we basically got it changed to this blue curve. So that's what we're expecting now. Instead of this awful 4.6, we're expecting a not quite as awful 3.2. So that's called basic progress in basically, what should we call it, management of governments. The basic concept is half a loaf is better than none. You know, this would be awful. So this is half awful. So that's what we've actually occurred. So we were pledging to hold it down to 3.5 degrees, and we actually got it down to the expectation of 3.2 degrees. So we're doing better. And this is how these things work. These big things don't get worked all at once. What happens is you get some agreement, okay, and you try it out, and people get to trust each other a little bit more. And then you get another agreement. So we'll now have an agreement that will basically take this business as usual curve and end up with some kind of curve in here. That's what COP28 will do. It still won't get to the goal down here, but it basically makes it less bad. So that's kind of what we've done. So this is a major goal. And let me show you how important this is so far that we've accomplished. So in order to meet the goal back in the 2015 goal, we would have to remove 1,000 gigatons of CO2. You all know the term giga because of computers. Everything is giga this, giga that. So it's 1,000 gigatons of carbon dioxide greenhouse gases. That's what our goal was. And so now we're to here, and we've already removed about half of that goal. We're already there. So instead of being in doom and despair, we should be having big parties, because what we're doing is we've gotten halfway to our goal. So now we only have to get rid of 500 gigatons of CO2 in order to be back onto this schedule here. So I would call that's real progress. So let's take a look at that then. Let's make a challenge. Let's say well, our goal was to get to 500. Let's double that goal just to show how confident we are. Okay, say we're going to do 1,000 because we want to have some padding here. So how can we do it? Well, what we do is we look up a cookbook that tells us how to do it. It's called Drawdown, the most comprehensive plan ever proposed to reverse global warming. And so what they do is they have a whole bunch of options. Do this and that, it'll save this much carbon emissions. Do something else, it'll save this much. By the way, this thing costs so much here, and here's your return on investment over here. So we use that as the guide. Now let's get some idea of what's happening here. This is how wind energy has been going. This is the US wind energy. The global pictures is similar. But basically, it's gone from nothing in 2001 up to about 140. This would be equivalent to about 70 San Onofre plants, okay, for wind by there. So wind can reduce on this time scale about 84 gigatons, which is a substantial amount because we have to reduce 500 gigatons or 1,000 gigatons. And it ends up that we save money by doing that. Because if we didn't do this wind thing here, we'd be doing something else with fossil fuels, and that would cost $7.4 trillion more dollars. So this is a giant savings. So what we can do is we're basically fixing up part of the problem, and we're making money in the process. So we can take this money and basically clean up some of our other social problems that we have. And Lord knows we have quite a few. So that's the idea. You basically try to find things that will be basically effective in terms of reducing the greenhouse gases, but also save you money. So that's rated number 2. Let's look at solar. There's different flavors of solar. This is a farm solar where you go out in the desert somewhere and you put a bunch of stuff up here. And here you can see we basically had none back here, and we're up to like 1,000 here in terms of gigawatts. So this would be equivalent to about 500 San Onofres. So it's taking off like crazy. This one basically for solar farms says we can save about 37 gigatons and save about $5 trillion savings. The rooftop stuff that you put on your own homes, that saves about 25 gigatons and saves about $3.5 trillion. So lots of good things happening here. You're getting your problems solved, and you're also saving money so you can spend that money on other things. EVs. We're seeing a lot of press on EVs. California's leading the way on EVs. The results here are that you can basically save about 11 gigatons of these greenhouse gases and end up with a saving of around $10 trillion. So these are really interesting things. So let's see, are we getting closer to the goal? Remember, my goal was 1,000 gigatons. That's the extreme goal. That's twice what we supposedly need now. So basically, we look at these three things alone here: the wind, electric vehicles, the roof, and solar farms, and that gets us to about 157 gigatons, saving 65 trillion bucks, and it gets us to 16% of our goal. So that's pretty good. And in what have we done? 5 minutes here, 10 minutes, we've been able to save a plan here for 16%. If we want to go to 100%, we have to go back into the drawdown book, go to their spreadsheets in the back, and add them up to this. It adds up to about 1,000 gigatons, which is the goal I used here, and it ends up saving $74 trillion. And by the way, with all this change in your pocket, you end up saving the Earth for humanity. Oh, question is, can we do it fast enough? Okay, we now know we can do it. This is also just using existing technology. Now, if we figure out how to do a better battery, that helps. If we figure out how to do a better EV, that helps. If we figure out how to do a better solar panel, like they're talking about making glass into solar panels, so you can cover all these glass buildings with solar panels. They're also talking about having ways to do solar panels that cover the median strips of your highways. Sometimes some of them are even working on the highway itself. So all those things would make this easier. So can we go fast enough? Or is the job just too big for us and we're going to sit back and go to Margaritaville and just decay? Let's look at LED lights. You all know about LED lights. Back in 2010, the ancient past, that would be 15 years ago, 1% of the lights were LEDs. In 2015, they're up to about 26%. 2020, up to about 70%. And they're estimating 2025 to be 95%. So they went from 1 to 95% in 15 years. That's pretty good in terms of the schedule that we have here. That means that can make a big difference. We don't want to have a technology that's going to take 100 years or 200 years because that's just too long for this time schedule. We need something that is effective in the here and now. This is a comparison of the cost of new electricity from solar and wind compared to fossil fuel plants, coal and gas. Okay. Back in 2014, which isn't that far ago, that's 10 years ago? Not quite. Yeah, 10 years. Solar and wind was cheapest in only 1% of the world. 1%. That means, boy, we're never going to make it. Okay. Bad adoption. By 2019, it became cheapest in 2/3 of the world. And the goal is that it should be cheapest everywhere this year. So that's pretty fast. That's going from 1% to everywhere in 10 years. So I think speed is not our problem here. It's just deciding to do it. So there we are, folks. We're getting near the end here. So I think I've tried to convince you that the climate crisis is an existential threat, that if you just sit back and don't do anything, that's too bad because you're just writing off humanity. I think I've convinced you that we have the technology and the economics to both conquer the problem and to simultaneously improve our quality of life. Now, we don't necessarily improve our quality of life because we're capable of taking all that money and squandering it on something else. It doesn't improve our quality of life. But if we are smart enough to use it for the right sort of things, and maybe people like you can help out with that, can make a difference. Now, the question is, do we have the vision? But people like you must decide. So this is a little bit of a biblical, someone wanted a little bit of a religious tone here. This is Moses's words to the troops in Deuteronomy. I've put before you life and death, blessings and curses. Now, choose life so that you and your children may live. So that's what an old leader of many thousand years ago had to say. This is a more current one, Thomas Jefferson. The price of liberty is eternal vigilance. So we have to act now. So with that, I thank you very much for your attention, and I'm looking forward to whatever questions you have during our final Q&A session. Thank you very much.
Okay. Wonderful. Thank you very much. That was wonderful. Tom has a question.
Well, it's a who question, and it's the we. And I had developed a rather glum outlook based on the state of the world is right now. Everyone fighting with everybody else, all these incredible divisions, isn't really good for that will making up a large mass of we, right? Of the who, if you look at it that way. How do you see those particular issues, those divisions, impacting the hopeful future that you have laid out? Tom, I'm Tom.
I think that is the question. Basically, what I've portrayed to you is a possible future. Okay, it's a future that I would love to see. Okay, now whether or not we choose that future, I don't know. I mean, I don't know how you predict the future. I mean, it's just like there's so many variables. But we could squander this on wars. We could squander it on all sorts of ways and not solve the problems. So the one thing I do know is that when you get a lot of people interested in the problem, it constrains the policymakers so that they don't do things that are too crazy. So hopefully, if enough people like you get involved in these issues, you basically will talk to your friends, your neighbors about these things. They will then think it's a socially acceptable thing to talk to their friends and neighbors about it. And pretty soon we have a lot of people talking about these things. And pretty soon what happens is the paths that are available to the policymakers get more constrained into paths that actually would make some sense for humanity. So I think that's the answer, that I'm hoping that we can get enough attention through organizations like yours that people will basically think this thing through, feel comfortable with the solutions, and tell their friends that this is what can be done. And hopefully that's enough to change it. If it isn't, that's sad. But I hope that's my hope.
Yeah, Tom, my concern is that sounds really good for the United States. But I was thinking about this and I'm thinking, well, let's see. That means we've got to get Netanyahu, if that's the correct pronunciation, and out of there. Putin, well, major revision there, or take out enough of their oil tank facilities that we can stop that problem going on. But you see the issue is there. That's great for a democracy like the United States. That's one country. And for a long time, it seems we've been pretty well committed to this, a place that will take us to the hopeful outcome. But then there's the issue of the rest of the world. Do you have any comments, what you think about the rest of the world?
Well, yeah. I think that you have to play ball with some of the bad guys. Okay. Basically, Russia's economy is based on fossil fuels. Okay. Saudi Arabia's economy is based on fossil fuels. Okay. You've got to recognize that you have to get these guys into the game in such a way that it is attractive to them. Not so that it's a burden that they have to take on and make this sacrifice for the good of humanity, but it's like, hey, we can make our economic numbers. We can, have a much more joyful group of people supporting us if we do this sort of thing. So that's the thing that it's called leading with the carrot. So we need to figure out some way there's a lot of money that's going to be used here one way or the other, either creatively or destructively. If we can take enough of that money to sort of bribe these guys into playing ball, then what will happen is we will then get their cooperation. But I don't think you need the whole world But I think you need maybe 5 countries. You know, Russia, China, U.S., Europe, India. If you get those in agreement, they can set up the economy, the economic deals such that everybody else will sort of like it, you know, at least go along with it. So that's the approach that I would take. I would basically try to have a carrot in this thing for these people.
Yeah. And there's a lot of landmass. Well, on the one hand, a lot of sunshine in 2 of those places. Well, that would not, like in Russia, a lot of landmass was at wind farms, right? And I don't know what their solar exposure is there. In Saudi Arabia, well, it's the friggin' desert. It's, and so they got a lot of sun exposure. So you have any thoughts about how these different possibilities, financial possibilities, as well
Yeah,
as
there are all kinds of schemes that are out there. I mean, the Saudis are basically pushing to build a major solar factory in Africa and basically have it connected to Europe through the island of Cyprus, I think it is, and then up to through Sicily and Italy and so forth. So that's that kind of stuff that people have priced that out. It looks very economically wonderful. So it's just a matter of, can you figure out how to get the agreements all made? Can you get the technology so that the cables, once they're laid there, won't immediately corrode or whatever? Will they last long enough to be useful? I think in terms of the solar stuff, that's pretty easy. You can pretty much take existing technology and stick it in Africa. It'll work. So I think that's one example of where you could have a near-term project that would make a big difference. Because what we're doing is, in terms of solving the problem, we're basically telling people get rid of a whole lot of the things you use now that use fossil fuels and replace them with things that use electricity. So when you do that, you basically have to have a heck of a lot of electricity available. So if you can make all that electricity available, like, for example, you could feed Europe electricity from Africa.
Yeah. Tom, how do you, and now we're looking at that, how do you see the storage of electricity issue factoring into it? It's got to be huge, challenging in that area, but what do you think about the potential impacts of that on that picture?
Well, wind, basically the winds come whenever they feel like. So you need some way to have some mild amount of storage for that, but not very big. Whereas the sun, we all know that the sun sets at nighttime and rises the next morning. And so you've got to have a heck of a lot of storage for that. Like California right now has an excess of solar energy. But we can't do anything with it because we just don't have the storage. So storage is going to be a big thing. So what happens is, if you have a big problem, usually a lot of people will start scrambling for the money associated with the big problem. And so you can anticipate that storage batteries will be very different than they are today. Like, for example, the Israelis run their tanks on aluminum oxide batteries. And my friends tell me that if you take one of their batteries and you scale it to a Tesla, that you could have 1,000-mile range with the current Tesla. So, there are all these possibilities, but God knows, maybe the aluminum oxide burns up or something. I don't know. But there are always problems with the new things. But there are always a lot of clever guys. So what happens is you have this economic incentive. You have a bunch of clever guys getting together, Silicon Vulture Valley places, and they basically go ahead and do some things. Some of it works, some doesn't. The stuff that works some of it may fail when it comes out at first, but some of it really works. So I see a lot of that going on with storage. So batteries are one way. You can just move rocks. You can have railroad cars in old mines.
Say it again, Tom. I'm sorry.
You can move rocks. You can store energy by moving rocks.
Oh,
You
yeah.
could have
Okay.
old mines and with rocks essentially, and then just when you have excess of energy, you move the train up, to the higher part of the mine, and then whenever it gets to be nighttime, you let the train go down, and as the wheels spin around, it generates electricity. So that's another way to do it. I don't think you're going to be able to do much with hydropower because we already have a ecological crisis with hydropower. And so, we're basically probably going to end up having less hydropower. But rocks are a good way to do it. You can do it with thermal storage. You can basically heat up something to high temperatures during the day, and then basically use that to generate electricity at night.
Yeah.
So I think there's all kinds of ways, but
So,
I think a lot of people are going to be looking for jobs because with this AI stuff, the kind of things that we used to do aren't going to be paying any money anymore. So
mhm.
you have to find something new to do in order to keep you occupied.
Yeah.
So I think there's going to be plenty of money in this, and so there'll be incentives for new folks to get themselves jobs into these new niches. So I think there'll be a lot of creativity. So we have the potential of making the Renaissance look like sort of just a beginning kind of thing. This could be much better than that, or we have the potential of basically making it a living hell, or maybe not even a living hell.
Yeah.
So it's interesting, and I think it's fascinating to me to be involved in this thing and trying to do
Mm.
my little bit like an ant pushing a log or something, trying to push it into a better direction.
Yeah, and again, another based on your sense of things, I was thinking of suggesting that I'll start praying that physics supports us in our storage issue, but and that being basically, I guess the idea was chemical storage, but it sounds like is your sense of it that is maybe just one factor, but these others are equally viable. There seem to be equally viable to this are facing the potential physics juggernaut, which are limitations on our ability to storage just for reasons of physics.
Yeah, and there'll be a host of problems like batteries. Okay, one of the things was making the press a lot was the shortage of lithium. My God, there's a worldwide shortage of lithium. Then someone discovers the Salton Sea is loaded with lithium.
Okay.
And so all of a sudden we may have, the world's lithium capital right there in the place that was pretty much useless.
Yeah.
So it's going to be a lot of unknowns, but I think it's a fascinating. I think it's the best game that I can think of being involved in, and it has the potential for the best outcome for humanity.
Yeah, I get it. That's great, Tom. Thanks. And to sort of sum it up in terms of that issue of storage, for example, which is huge. To somehow sort of the pressure. There's a lot to be seen. To sum up what you said, there's a lot yet to be seen.
Yeah.
So we
And
have
just think of what this could do to education. So what you do is you start having professors getting involved with their students in storage, for example. Or you have another group of professors being involved with how do these ecosystems work that are turning into deserts? Is there some way we can turn them into verdant green areas by taking advantage of our knowledge of keystone species and how the ecosystem, the mathematics of how an ecosystem really works? Can we basically start making everything much, much better as opposed to making everything worse and worse? So I think there's a lot of intellectual opportunities that are just sort of just sitting there waiting to be captured.
Thank you for all, Tom.
we're almost at the end here, so we got a couple of people ask with questions. Let me call in Julia first because she hasn't asked a question yet. Julia.
Okay. Am I on now?
Yeah.
Okay. So thank you. I'm much more optimistic now than I was before your talk. And I appreciate that. However, my hesitation is that you're preaching to the choir, with the presentation to this group in particular. And I would assume that others are like me in that they do talk to their friends, and we do talk amongst ourselves and whatnot. But just like with the LED application, the reason that worked is because people weren't just thinking globally of saving our planet. It was because the LEDs saved the money and electricity was getting high. So how does one make the things that you're suggesting, solar and wind and all of that, it's all happening and it's wonderful, but it requires a tremendous outlay in order to save this many $1 trillion, we have to spend this many less $1 trillion. And the motivation, I mean, I'm a psychologist, so, insight's not enough, as Jamie would say, in his book. It's how to motivate people. Do you ask my what?
Financially motivate.
Financially, I'm at Sharon's house. How to financially motivate people, because I think that's almost the only thing that really is going to change.
Well, let me have a shot at it. I don't have the perfect crystal ball, but I'll give it a shot.
Yeah, please.
Let's take an example of EVs and solar systems. Those are two
Mhm.
examples I'll go through. EVs first. You got this car that's much more comfortable, much more quiet, much more powerful, much cheaper than anything we used to have. Okay. People are going to like that. Okay. So they're going to buy a lot of those things. So unless we really foul up the marketing, people will go from that and they'll ditch whatever they have. So that I think that economic piece is there.
Well, I agree theoretically, not even theoretically. In California, that's true. If you want to spend $50,000 on a car, I would love to be able to buy an electric car. I'm in the group that would like to do that, but the majority of people, I think, and I could be wrong, I don't know.
Well, let's take the car price. For example, Chevy Bolt.
Right. Oh, that's true.
It's going for a price that'll be under 30K. Okay,
Yeah, that's true.
with all the discounts.
Yeah,
So, and that car, that's what I have, a Chevy Bolt.
right.
And the thing is, the best car I've ever had.
A good point. So I guess you're saying that you think that things are rolling pretty well in terms of people's motivation?
Yeah, the only problem is manufacturing. They can't get the manufacturing together yet because it's all too new and it's too much and so forth. So it's a real strain on our creative abilities. But I think the financing is there.
Okay.
So let me take that as a victory and move on to solar. Okay. Now, right now we have a disincentive for people to put solar on their roofs. Basically,
Right.
the utility,
The
God bless them,
subsidies changed.
is doing everything they can to basically make it so you'd hate putting a solar thing on your roof. Okay. And so we need to make a political change there where we change the rate structures to the utilities so that putting a solar thing on your roof is attractive to you because you save all this money. Like,
Well,
for
we
example,
have that, but then the electrical companies, we got rid of it.
well, they took it away. So
Well,
this
exactly, because
is
they
now a
were
political
losing
question.
money. Yeah.
It's a political question. So people
Right.
like you need to use their influence to basically maybe have the PUC commissioners thrown out, maybe abolish the idea of PUC and have all utilities generated like they do in Palo Alto, where the city runs it.
Mhm.
There's a whole lot of options, but basically you need to let these guys know that it's in their interest to play ball as opposed to trying to steal all the marbles.
Mhm.
So that's how you win on solar. You have to make it so that whatever you do with solar technologies, whatever, it has to be attractive to the average bear. So if you do that, you win the economic game. It's not a technology issue. It's just an issue of how we
We know that.
slice up the energy pie.
Right. Okay.
Those are two examples.
Thanks.
Okay, thank you. Alvin, last question.
Okay. So, again, just make a brief comment on something I said earlier about the rest of the world being the problem and not the United States. I think that's a little too sanguine. I think there are a lot of political forces and economic forces in the United States that are not on the agenda with this thing, and I think it's not completely clear yet what the overall outcome is going to be on that issue. So I'll just make that's the point of view I have. But on the question, I see most of what you talked about is basically lowering emissions, but there's another part of the equation from scientific and maybe even economic point of view, and that is absorption of carbon dioxide as opposed to cutting emissions, throwing into the mix mechanisms for absorbing carbon dioxide more effectively out of the atmosphere. Maybe you could just say a couple of words about that.
Yes, I think that's a very poignant thing. The graphs that I showed you were basically based on getting to a temperature rise of 2 degrees as opposed to a temperature rise of nothing. Okay. Now, what that means is we're stuck with whatever the atmospheric conditions are with flooding, hurricanes, whatever that are associated with 2 degrees. And that is going to be an unsatisfactory place to be stuck. Okay. So you need to have some machine that comes and sucks the CO2 out of the air. So now, whether that machine is something that looks like a factory or it looks like a jungle of Brazil, I don't know. You know, there's lots of options, but we're going to have to, once we get to this place of where we haven't wrecked the whole place, we just messed it up a bit. You know, we're going to have to get to a place where we say, let's get back to something that's actually desirable. And that's going to mean sucking the CO2. You have two options. You can wait 1,000 years, which is what the normal process takes. Okay, or you can basically make machines or plants or agriculture or something to remove the CO2 at a faster rate. And if you do that, I'm hoping we can get it to it'll be like a 50-year kind of thing as opposed to 1,000-year kind of thing.
And in addition to that, it seems to me, right aside from saying, okay, we hit this level, but now it's going to take a long time to get rid of the CO2. Let's get rid of it. It's also part of the way of reaching the goal in the first place. Because if you pull CO2 out of the atmosphere and cut emissions, that's better than just cutting emissions as you try to achieve the goal. Is that reasonable?
Well, yeah, I mean, it's a combination. You know, if you had some effort on removal of CO2, along with an effort to reduce the amount you're throwing into the atmosphere, okay, then that would basically be the smart way to play your cards. Right now, I think that we're just so overwhelmed by just getting the first part done. You know, basically, you cut the emissions down, that we're not putting enough money into the let's get the thing out of the air. And unfortunately, the politics of let's suck it out of the air is being played in a way where it basically is saying, instead of let's really make this thing effective, let's just use this to expand the lifetime of these fossil fuel plants.
Mhm.
So the politics of that gets a little dicey, and it's hard to thread your way through all of that. But I think those are the pieces.
Thank you. Appreciate it.
Dorothy, did you want to ask something?
Yes, I was just curious what the faith community down in San Miguel de Allende, what they're interested in this is and what their plans for action were.
That's a great question. Jürgen, are you still with us?
Yes.
I am, yes.
Would
Well-
you like, go
Well,
ahead.
San Miguel is a magnet for a lot of people from all over the world because it is a unique city, World Heritage Site. It is arid land. We have very limited water, very limited potable water, certainly. The city has not done very much as far as an environmental plan. There are at least 14 or 15 NGOs that are environmentally aware. And just recently, I wrote an editorial that hopefully will reach the mayor's office about we need an environmental plan because we are killing the goose that laid the golden egg. There are more and more people being drawn to San Miguel and houses being built, compounds or communities being built, gated communities being built. But the water supply, just for example, the water supply, but the air pollution also is getting increasingly worse. And my hope is that we will have some kind of environmental plan in place that reflects some of the IPCC's projections for 2030, 2040, and so forth. Right now, from a municipality's point of view, we're not doing anything. We have diesel buses that are spewing a lot of emissions in the very narrow cobblestone streets of San Miguel. And, but there are definitely growing individuals, growing people, and organizations that are beginning to act together. And I think that can be hopeful in the future, in the very near future.
And I would say also a basic tenet of our faith is that we believe that humans and other live creatures are all in this planet together. And so we do not see it as separate from our faith to not be active to promote the well-being of all creatures.
I'll add to that the state in which we are, Guanajuato, is the most conservative state in Mexico, and the Pope is not a very popular Pope. Pope Benedict was very popular in the state of Guanajuato, and the encyclical or the paper that Pope Francis published is not getting very much attention through the churches. The churches are still very strong in Mexico, as you can imagine. And culture is an amazing force for action or inaction.
Yeah. Thank you.
You might want to take a look at what they've done in Costa Rica in terms, because they've had similar issues in front of them, and they have made a marvelous transformation there. So maybe that might give you a little bit of a template of
Cartagena?
No, Costa Rica.
Costa Rica, thank you.
Okay, unfortunately, I think we need to put a stop to this. We're way over the time, but anyway, we want to thank Tom for his